All right, so at this point, we have talked about the basics of NMR as far as being able to look at a organic structure and determine the number of signals that actually come from that organic structure that would be represented on an NMR spectra. And we're going to take this another step further eventually, but there's still some terminology that we're going to have to take care of before we go into that next step. And we're going to start tying all of these loose end pieces together finally. So here in the computer screen, you'll see an image of an NMR spectra that we worked with in the last video. And there's two signals, there are two major signals, and we talked about where those signals come from, or really what we call chemical shifts. And we also talked about this unit of part per million, which is down here at the very bottom. So that part per million is actually in terms of hertz and megahertz, and that's how we calculate the typical 0 to 12 x-axis that we normally see. You know, here they stopped at an 8. It's not a big deal. If there's no more that happens after a certain number, then very often in these images, they'll just kind of chop it off at that point, and they won't really report any of that value after that part per million level. Just to make sure it's cleaner, making sure that you put a focus on the major signals that you should put a focus on. But terminology-wise here, there's areas of this chart that we want to go back to, talk about, bring in some other verbiage that we've used before in other videos at this point. And the first one that I want to talk about is this idea of upstream and downstream. All right. We also are going to talk about this idea of up chart and down chart. So if you look at the axis, you're seeing that frequency increases as we go left. So this should not be surprising, right? We've got a 0 to the right-hand side, and then a 1, and then a 2, and then a 3, and a 4, and a 5, and a 6, and a 7, and an 8. So as we go from right to left on almost all NMR spectra, we are increasing the frequency as we do that. And that frequency is in terms of this hertz, really, that is the distance of how far it is from the TMS signal. So if we look at this area to the right-hand side is going to be called Upfield. And the area to the left-hand side is going to be called Downfield. So the way that I want you to remember this, think of yourself on a football field, and you're the 0 mark. You're the TMS. And someone says, throw the football. And if you're like me, you're like, I don't know how to throw a football. And I'm proud of it. But if you throw the football all the way down the field, as far as you can put it, do you see what I did? We're going to throw the football all the way down the field that we can. That means if you are the TMS, hey, hi, if you're the TMS and you're throwing that ball down the field, the further you go with it, the further downfield you're going to go with it. That is why this is called the downfield. The left-hand side in an MR is called downfield. The right-hand side is called upfield. You only have to remember one. Remember the downfield. It's the easiest. It's further down from you if you are the TMS molecule. This area also has the highest frequency. That should not be a question that you get wrong on a test. And the reason is because it's telling you that down here, these numbers are higher. 8, 7, 6 versus 1, 2, 3. They're higher values, they're higher ppms, therefore they're higher frequencies in order to get those higher ppms. So downfield is to the left, and the downfield area, the more downfield you go, the more frequency, the higher frequency that you're going to find these molecules. You're also going to find all of what we call the deshielded molecules, or the hydrogens, really, the protons. in the downfield area. Okay. Now, the deshielded, really not something that we've gotten into that much. We've talked about the idea of neighbors. We've talked about the idea of the neighbors screaming, "Ah!" along with the kids. And those neighbors are going to become important. We just really haven't made it that far yet. We've only counted the number of kids on the swing. We didn't go any further than that yet. That's it. How many kids are on the swing set? How many kids are screaming in a different way? But these kids, these neighbors, they're going to affect the way that the kids scream and the way that we pick them up. So that is still a conversation to have another day. But when we get to that point, I want you to understand that the kids that really don't have neighbors, they are the deshielded ones because nothing is around them. They're more exposed. And those deshielded kids that are on the swing set, they are getting picked up downfield. If the kids have neighbors to them, then they are shielded. And if they are shielded, they are more on the upfield side. So the upfield of the NMR has the shielded protons. They have very low frequencies and these really tiny ppm values. Whereas the downfield side of the spectrum has the higher frequencies, the deshielded protons, and the higher ppms. All right? So that is the conversation that we had to have before we go further, because again, we're going to start tying all of this information up together. So now we know a couple of things in NMR. Okay? Let's list them. What do we know? Well, number one, we kind of know how NMR works. It's a machine. We put a sample that has been mixed with TMS into the instrument. A couple of magnets. Attention! Get all the molecules to line up. And then we start to pump in frequency to this thing. And these molecules begin to swing on their swing set. And then sooner or later, those molecules flip upside down on the swing. And the little kids go, "Ah!" And then we hear that sound. And then the NMR picks up that sound. And it gives it to us as a chemical shift. We're able to pick out the number of kids already. Number two, we now know what the typical spectra looks like. The x-axis has ppm value. That ppm value is in terms of hertz over megahertz, and typically it goes in the range of 0 to 12. 0, though, is over on the right-hand side, and it increases as you go left. So it is a backward axis for NMR. We also know the units. We just talked about them. I just mentioned them. And that is the delta, or this ppm, or this hertz over megahertz unit that we can use in NMR theory. And then number four, we've also talked about the number of chemical shifts, right? That's pretty important. We did 2 or 3 videos just on being able to determine the number of chemical shifts that happen from a compound. So now we're going to have to go a little bit deeper, and we're going to have to answer a question. And that question is, how do we know which protons correspond to each signal or shift that is on the NMR? That's the next connection point for us. What does that even mean? Okay, well, let's go back to this. We've already done this problem. We said there's a signal here and there's a signal there. And look, there's a signal here and there's a signal there. Okay, that's great. But how do I know which is which? So for instance, this CH2 group. Is that CH2 group this signal or is it this signal? And is there a rhyme or reason on how I can figure this out and predict this lineup before we're even given the NMR, right? How do I make sure that this thing is going to match the way that it's supposed to match? That is what this next topic is going to be about, right? We know how to determine the signals. We know how to look at structures. We know how to look at NMR spectra, but how do I match them? That's the key. All right. Well, there's a few things that we can do that will make our life a little bit easier, even though this is going to be kind of aggravating. And the number one topic here is electronegativity. How greedy is the atom? So if there is an electronegative atom, the protons that are around that atom will appear downfield. We need to talk about why. So this will give us our first indicator of positions. Where will the shifts happen? How do I put a little bit of theory behind why is this shift located here for these protons, and then these protons give me a different signal, and these will be more upfield or these will be more downfield? How do I put a backing? How do I put an explanation behind all of it? Well, let's take a look. What is this saying? Well, if we've got a molecule, I don't really care what it is, and then this molecule has an electronegative atom. All right, well, that electronegative atom, let's say that it is an oxygen. Oxygen's electronegative, right? So let's say there's an OH group on here somewhere, and then this is a carbon that has an OH group. Let's say that this carbon has a hydrogen on it as well, and then next door is a carbon with maybe a hydrogen here and a hydrogen there. So we want to compare these signals, right? So I know that if I don't give you any more information about the structure at all, I know that we're going to see a ding ding, a structure that is here that's going to provide me a signal, and then ding ding, a structure that is there that's going to provide me another signal at least. Whatever else is happening in the structure, I really don't care. It's all just a matter of comparing. That's what we want to do right now. We just want to compare, and why are things happening the way that it is. So I've got two different signals, two different chemical shifts that will happen in the NMR. One will happen at one location and the other will happen at another location. And we just talked about this concept of what NMR actually means as far as the spectra goes. So this to the left-hand side is downfield, because here's the 0 mark. That is where you are. You're the TMS, and you're going to be throwing the football down the field, and the further it goes, the better off that your throw is going to be, right? This is what is downfield. So this rule says if there's an electronegative atom, there's the oxygen, that's electronegative. The hydrogens around that will appear downfield. Here is a hydrogen that is connected to a carbon that is on that OH group. That hydrogen is going to be affected. Why? What does electronegativity mean? Electronegativity, that's what that means. It sucks electrons. It loves little electrons. The more electrons, the better. So this proton that you are seeing at this spot, that proton is going to put up a fight against the oxygen, and it's not going to be a very good one. So I'm seeing all of the electron pull that's happening here with this electronegative atom. And that means that this hydrogen is very exposed. If that hydrogen is very exposed, because that oxygen sucked all the electrons away from it, then this hydrogen is exposed to what? It's not exposed as in, oh my God, I dropped the towel and I just got out of the shower. That's not what it's exposed. It's exposed to the magnetic field. That is the magnetic field that the machine is putting on this compound. That magnetic field is going to hit this proton more. So this magnetic field is going to be able to look at that proton and grab a hold of it as strong as it can. It's more exposed. So therefore, when this machine does what it needs to do and it starts going through the hertz, and it's doing 1 hertz after another, after another, after another, it's going to keep flipping more and more and more hertz until it can get that hydrogen to flip upside down. And because it's more exposed, it's going to take more hertz in order to do it. It's going to take more pushes in order to flip that hydrogen upside down so it can go, and we can pick it up in the signal. So that means that the downfield signal will be more appropriate for that hydrogen. Okay? The carbon next door, this carbon is further away. This is going to give us a different signal. We already said that. These hydrogens, they might be a little exposed, but not as exposed as that one that's connected to the OH. So these particular hydrogens, because they're not as exposed, that means the magnetic field that we place on them is not going to grab them that strongly, which means that as the machine begins to flip the hertz, one after another, after another, after another, after another, it doesn't take as many pushes in order to get those to flip and all the way back down. So because we don't have to do as many pushes, we actually see a signal like that more upfield, meaning closer to the 0 mark. That is what this is all about. So if you go back and take a look at some of our terminology that we just did, we talked about this idea that these unshielded or deshielded atoms are going to be more downfield. The shielded ones, which means has more things around them, the magnetic pull, attention, doesn't lock onto them that well or as much. It doesn't take that much to flip them to get them to scream. These are more on the upfield side of the spectrum. Okay? So there's our number one kind of initial starting key connector here between electronegativity and what is exactly on the compound. The more electronegative those atoms are, well, the less shielded, more exposed that those protons are going to be on that particular carbon. All right? So, with that said, let's take a look at an example problem. Let's take a look at actual numbers and a structure that begins to happen here. And here's one of them. So in this structure, it looks like I've got a CH3, a CH2, a CH2, and an NO2. This NO2 group, well, these are electronegative, folks. I don't know about you, but I know that at least. And this NO2, the oxygens are going to be electron pullers. The nitrogens are going to be electron pullers. I mean, this is an electron puller suit right here. So the hydrogens that are closest to those electronegative atoms, these are going to be more exposed. What on earth has happened? Those are more exposed. Because they're more exposed, they are more de-shielded. That's what that means. Not a lot of things are around them. They're exposed. And if not a lot of things are around them, then that means they don't have anything shielding them. So they're deshielded atoms. They're deshielded protons. And if you look at that number's 4.37. That means 4.37 ppm is where this thing is going to show up on the spectra. Now, if you go further away from that electronegativity group, you're seeing that these protons are a different signal, and those protons are 2.07 ppm. The reason for that is they're further away. And because they're further away, they're not as exposed. These electronegative atoms are not pulling electrons away from their orbit. So these hydrogens have more of a cloud. They have more things that are around them. Because they have more things that are around them, they're more shielded. And because they're more shielded, they're going more and more upfield or closer to the zero mark. And then finally, our third signal is coming from here. And this is the furthest away from that NO2 group. And because it's furthest away from the NO2 group, that NO2 is really not pulling electrons away from them at all. At least not that much. So because they are even more clouded, even more neighbors that are surrounding them, they are more shielded. And the magnetic properties of the NMR cannot grab a hold of them that well. They are shielded from that magnetic field. And because they're shielded, they are more upfield, and you're seeing a 1.04, very close to the 0 TMS number. And again, the reason for that is because it doesn't take a lot of energy to get these to flip. That magnetic field is not pulling on them that much. They are surrounded by neighbors, as well as electrons. Those include neighbors, right? Just because you got a neighbor next door, if they've got 20 kids in their house, well, every 21 of those kids, they're going to be neighbors. Doesn't matter how little they are. Same way with electrons. Doesn't matter how little they are. They're still neighbors. It's still shielding you from everybody else. So that is one of the key predictors that we can use to determine which signal is which if we've got to explain it in some form or fashion in an NMR. Now, down here at the bottom, you're seeing a molecule, 1, 2, 3, 4, 5 carbons with an F, the same molecule with a chlorine, the same molecule with a bromine, the same molecule with an iodine. Notice that your F is the most electronegative out of the chart. That was one of the first Orgo 1 lessons that you ever learned. Actually, it was probably one of the first, or should have been one of the first, general chemistry lessons that you ever should learn. So because this is the most electronegative, it is the most electron greedy, which means that this particular carbon that's next door, those protons, that fluorine's going to do more sucking than the chlorine, which does more sucking than the bromine, which does more sucking than the iodine. So these hydrogens are way more exposed versus everything else. And because of that, you're seeing that 4.50 right there. It is more on the downfield side of the chart because they are more exposed to the magnetic field. That means it's going to take more energy in order to flip them because they're more exposed to the magnetic field. Chlorine's less electronegative, so the ppm went down. Bromine's even less electronegative, the ppm went down. Iodine's less electronegative, the ppm went down. So you are seeing a very strong tie here between electronegativity values and the way that it basically exposes the protons that are neighbors to that particular carbon. This slide also shows you the concept of bulkiness as far as compounds go. It's not just all about electronegativity. So what we're showing here at the very bottom is this carbon that is a tertiary group, right? I see 3 carbons attached to that one and a hydrogen. And then this one, more of a secondary carbon. It's connected to 2 others. And then this one, more of a primary carbocation. It's only attached to 1 other carbon. So if you look at the groups and the way that these other groups surround those hydrogens, again, it's all about the hydrogens for NMR. How does this play a role? Well, let's first take a look at this one. These hydrogens, not really surrounded by too many neighbors, right? There's no electronegativity groups on here. We're just looking at carbons now, just bulkiness of compounds. There's just one carbon and that's it. So these hydrogens are not that exposed, or are they, compared to this one and compared to that one? Well, the one over here to the left, this has 3 neighbors. These 3 neighbors kind of are right there with that hydrogen. Those 3 neighbors play a role in how this hydrogen basically sees the magnetic field. And it looks like this one has a higher ppm value, which kind of means that this one is more exposed. And this one has a lower ppm value, which means that this one's kind of the middle exposed. And then the last one has only 1 carbon with a 0.85. And this one is the less exposed out of the 3. I can talk about this in terms of shielding as well, because this looks like this is on the Upfield side of the chart. It's closer to the 0. And we've already said these are shielded and these are going to be deshielded. So the question here is, why is this happening? That's kind of strange, right? I mean, at first glance, it looks like this carbon with that proton has 3 carbons on it. So these are big bulky groups that are surrounding that hydrogen. If these big bulky groups surround that hydrogen, then wouldn't that make the hydrogen less exposed? Which means that the magnetic field is going to be applied to it not as well, which means it won't take as much in order to get it to flip. And these, the more exposed that they are, isn't that kind of what we've been saying all this time? So to explain this situation, we're going to have to introduce a new rule, all right? So the very first rule was this idea of electronegative atoms onto a molecule. The next rule that we're going to look at, a very general rule in NMR, is the lower the number of hydrogens that the carbon has, the more downfield the signal becomes. And this will help explain what we saw in the previous lecture slide. So the lower number of hydrogens of that particular carbon, the more downfield the signal becomes. What that basically means is that it's not just about the bulky atoms that's around the carbon that will kind of help determine where the locations of these particular signals are going to be. It's not about the idea of bulkiness of a group or how many things surround the hydrogen, because this is why. If we take a look at the hydrogen, and that particular hydrogen is surrounded by an electron cloud, that's the key. It's the electron cloud that prevents the hydrogen or exposes the hydrogen to NMR. If the electron cloud is there, then we feel pretty good about where the signal lies, because that electron cloud will help cover up the proton. If we don't have an electron cloud, that electron cloud will be sucked away and the proton is more exposed. So it's not about bulkiness. It's about the electron density around these protons. And these protons are going to play off of each other. So the lower the number of hydrogens, well, that means that these hydrogens are going to be more exposed. And those more exposed hydrogens will kind of experience a stronger magnetic field with the NMR instrument, and it's going to take more energy in order for them to flip. So that means their signal will be more downfield. And that's what we're seeing here. So in this very first example, we see hydrogen here, but the very first rule was all about electronegativity, basically being sucked, electron clouds being sucked through. That is not what these are. There's no electronegative group on these compounds at all. It's all about the number of hydrogens. So the lower number of hydrogens, the more downfield this signal will be. So this particular carbon has one hydrogen only. So this one's a little bit more exposed. This one, there's two of them. So those two hydrogens are going to play off of each other. And then the third one, you'll see three hydrogens here. And those three hydrogens will play off of each other even more so than the two and more so than the one. So these three hydrogens, they are less exposed to the magnetic field because it's all about proton structure here. And because they're less exposed, they're side by side by side, they're going to have a more shielded, more upfield as far as signal goes versus the other two examples that we see here on the screen. All right. So if we take a look at the NMR of that compound that we were looking at, notice this says methylene protons and this says methyl protons. So this carbon has 3 protons, right? 3. So there are more hydrogens on that particular carbon. And because there's more hydrogens on that particular carbon, the signal is going to be more upfield versus some of the others. This particular carbon has 2 hydrogens. So those 2 hydrogens, there's not as many as 3. So because of that, 2 hydrogens, the exposure is a little bit more, and that signal is going to be more upfield or downfield, more downfield as compared to the first one. Also note the number or the quantity of hydrogens are also very important. So if we look at the 3 hydrogens on that carbon, we said this was the same signal and that was the same signal. So we're getting a total of 9 hydrogens that are here versus a total of 2 hydrogens that are here. So if you look at this particular signal, we now know that there's more hydrogens involved. More hydrogens involved mean more upfield. So this signal is much taller, and the reason is because the quantity of those hydrogens are much more versus the methylene protons, and the methylene protons would be from the CH2 group. So there's only 2 hydrogens there. Those 2 hydrogens mean the signal is going to be more downfield compared to the others, and because of that, we see a signal here at a higher ppm than the other one. Not only that, but there's only 2 of these protons, and if you take a look at the intensity of that signal, it is much shorter compared to the first one, and that is a sign that we have less amount of hydrogens in this particular signal from that particular hydrogen equivalency than the prior one. All right, so again, we're slowly weaving the pieces together. This is not the last time that we're going to see this, though. We're going to keep this up in more example problems in the upcoming videos.